Strong and weak acids and bases. Strong acids versus weak acids. So with a weak acid, essentially what makes it weaker, what defines it as weak, is that it will only partially ionize. And so when you put it into water, it's going to let go of hydrogen ions as any acid would. It'll donate protons, let go of hydrogen ions. But what defines it as a weak acid is that the extent to which that happens is not 100%. So imagine if you had a bunch of these acetic acid molecules, you put them into water, and a lot of them are going to just stay together. They hang on to their hydrogens. But some of them will actually let go of their hydrogens. As a group, at any given time, some of them will have let go of their hydrogens and other ones will have not. That's what defines them as a weak acid, the extent to which that happens. Weak acids, that only happens a little bit. With a strong acid, so you put something like HCl into water, we assume all of them will dissociate. So every HCl that you drop into the water, it will all separate into hydrogen ions. You put 1,000 of them in, you get 1,000 hydrogen ions, 1,000 chloride ions. But with acetic acid, if it's only like 1% ionization, then if you put 1,000 of them in there, you're only going to get 10 of them at any given point that have dissociated. Now, there's nothing special about the 10 that have dissociated. It is an equilibrium system. It is constantly going back and forth. So it's not that 10 will dissociate and they just stay dissociated. It's that 10 will be dissociated. If it's a 1% ionization, 10 out of 1,000 will be dissociated at any given point, but it will be constantly going back and forth. So if this guy right here is the one that dissociated, it would stay like that for a while, and then it would pick back up its hydrogen ion, and some other guy at some point would dissociate, and it would be the one that is dissociated. Partial dissociation for weak acids, complete, or at least close enough to complete that we just pretend it is complete, dissociation for strong acids. So the weak acid, again, it's like there's, with the strong acid too, it's like there's a competition for that hydrogen ion. The question is the anion of the acid going to be able to hang on to the hydrogen, or will water be able to take it? And so think of it as a competition. With weak acids, they're better at hanging on to their hydrogen ions. They are better at competing for that hydrogen ion than water. With strong acids, they're not that good at hanging on to the hydrogen ions, so they will lose them. So weak acids have a strong hold on their protons. They don't give them up that easily. And if it's something like less than 50% ionization, then we'd say, okay, that's a weak acid. It's got a pretty good hold on its hydrogen ions. Therefore, when you put it in the water, there's not going to be all that many hydrogen ions in that water. However, with strong acids, they have a weak hold on their protons. They let go of those protons very easily. So you put a bunch of them in water, you put 1,000 in there, all 1,000 will let go of their protons. And so we have close enough to 100% ionization. We assume that that reaction goes to completion. Thinking of this as an equilibrium system, with a strong acid, we have a full shift to the right, whereas with a weak acid, we have some shift to the right, but then there's also some back and forth between the right and the left. And depending how weak the acid is, there'll be some amount of reactant still and some amount of product. Again, it doesn't have to be equal at equilibrium. What's equal is the rate at which they're going between them. And so once an acid has dissociated, you get some amount of dissociation, and then you have some amount of acid that's still together and some amount of acid that has dissociated. Whereas with strong acid, we just assume they all go and produce the products, and you have a full 100% dissociation. So because weak acids don't fully dissociate, we'll have some appreciable amount of original acid left, and we'll have some amount of ions formed. And the system's going to be in equilibrium. So of course we can set up an equilibrium expression for this reaction. And just like any other equilibrium expression, it's the concentration of the products over the concentration of the reactants. And you may notice that water is not included in this reaction. We could put it on the product side as H2O. And of course, if we did that, this hydrogen should really be written as hydronium. Often out of laziness, we don't do that, but just realize that water is always involved in this. It's the water that is taking that hydrogen ion from the acid. It wouldn't just do this on its own. It's water that's taking it. But because, again, water's a liquid, its concentration is not going to change, so you don't see it showing up in the denominator here, and therefore it's kind of easy just to put the H there and then have everything nice and easily balanced out and just pretend the hydrogen ion's free, though in reality it is actually attached to a water molecule as a hydronium ion. So what this is going to tell us is that the weaker the acid is, the fewer products you're producing, the less ionization there is, the lower the concentration of the hydrogen or hydronium and the anion, wherever that happens to be. Remember the generic expression for a acid dissociation, you can just put HA. If it was like acetic acid, then you could actually write that in and say, okay, I'm going to actually write the acetate ion in. Or you could just say, okay, that takes too long, I'm just going to write A instead. And so when you write the equation, feel free to use a generic one or use the specific acid, doesn't matter. With the weak acid, though, there's going to be some amount of products, there's going to be some amount of reactions left over. The weaker the acid is, the fewer products are produced, the smaller the numerator, the greater the denominator, and therefore the smaller the K value is. Because these are acids, they get a special little denominator there, or a label, I guess, for the K value. So we call this the Ka, which is the dissociation constant for the particular acid. And again, the lower the Ka value, the less dissociation there is, the smaller the percent ionization would be for the acid. Bases, same thing. So bases, again, bronze and iron bases, are going to be picking up hydrogens, and so you can imagine them acting on the water. If this base here is going to take the hydrogen from the water, it'll leave behind the hydroxide. And so when we set up our equilibrium expression for this, we're talking about weak bases here. And so what they will do is they'll take some of the hydrogens from water, but not all of them. So we'll end up with some amount of reactants, we'll have some amount of products in equilibrium, so we can set up our equilibrium expression. Of course, we're talking about bases, so it gets its own little subscript B here. But just like any other equilibrium expression, we have the concentration of the products over the concentration of the reactants. Water being a liquid with a constant concentration is incorporated with the K value. It doesn't show up in the equilibrium expression. You don't want to have an expression with two constants in it. And so water is essentially neglected there, but it is incorporated with the K value. So exact same as any other equilibrium expression, but specifically regarding bases. And then we can look at the OH values here in the future. Kb is referred to as the base ionization constant, same as the Ka, really the same as any other K value for any other equilibrium expression. It just happens to be talking about bases in this case. These values, again, because acids and bases are such an important part of type of reaction that we see all over the place, often these Ka and Kb values will be given to you in a particular table, and so you can look them up for any given acid, or maybe they may be given in the question, or if you have the concentrations at equilibrium, you could use that to find the K values. Looking at this table, again, remember the smaller the Kb value, or the smaller the Ka value, the less dissociation there is, the less of a shift to the right there is before equilibrium is established, meaning it is a weaker acid or a weaker base. It doesn't go to completion. So the ion product constant for water, any of these acid or base reactions are going to be taking part in water, and so they're going to be essentially changing the makeup of the water. So it's important to understand what the water is like before this happens, and then we can start talking about, okay, well, what's going to happen when it starts changing the way water is. So we know water is amphoteric. So one of the neat things that it does is it autoionizes. So if you had a bunch of water sitting in a jar, you're going to have some water molecules, and because they have the ability to both donate protons and accept protons, some of them will have done that. Some of them will have donated their protons to the other water molecules that have accepted their protons. So it seems a bit weird, but basically a water molecule will take the proton from another water molecule, creating some hydronium and some hydroxide. Now, this is called the autoionization of water. Water autoionizes itself. And so it will take a proton from one to the other. And again, this is going to be an equilibrium system. So we're going to have some extent to which this shifts to the right. It is a very small extent to which it shifts to the right. The K value for this reaction, which we're going to call the Kw because it's aqueous solutions are very important. So water is always something we're talking about. And so this particular equilibrium that water is normally in, it has a K value that is particularly called Kw. But it is a very, very small value. The left side of this is strongly favored. It's not that easy for a water to take a hydrogen from another water. It will be happening, but there are going to be a lot more waters on the left-hand side of this reaction than there are on the right, and so essentially the K value is quite small. The reaction, or equilibrium expression, sorry, would be, of course, the product over the reactants, but because both of the reactants have a constant concentration, they don't show up in the equilibrium expression. They're incorporated with the K value, in this case the Kw value. So really Kw is just the concentration of hydronium multiplied by concentration of hydroxides. And we refer to this as the ion product constant for water. And again, it's better to write hydronium, but often people are lazy and they're just going to say, okay, I'm going to balance it for only one water sort of breaking apart, even though that wouldn't really happen that easily. It is one water taking from another water, so you end up with a hydronium, but often you'll see it written, and I will do it too, just with the hydrogen ion instead of this hydronium ion. Anytime you see a hydrogen ion, just realize they're just being lazy. It really is hydronium. So in pure water at SATP, room temperature, it turns out that the concentration of hydronium is also equal to the concentration of hydroxide. That's why water is neutral. The concentration of hydrogen ions, or hydronium to be proper, and hydroxide ions are equal. And it works out that they are 1 times 10 to the negative 7 moles per liter. So now you can drop that into the equilibrium expression for the autoionization of water. And you can see that the value, the K value for the autoionization of water is 1 times 10 to the negative 14. You may recognize that number. And so all aqueous solutions are going to have this K value. And again, this is as long as you're talking at 25 degrees Celsius. And this is a constant value. And so what this allows us to do is work with aqueous solution and start saying, okay, well, if this is true, when we start adding acids or bases into this water stuff, then it's going to start messing with the equilibrium of water. The concentration of the hydrogen ions, or hydronium, and hydroxide ions will start to change, but this Kw has to hold true. And another way of thinking that is, if we know that this Kw value is constant, then what we can do is we can start figuring out what the concentrations of hydrogen ions are, or hydroxide ions. If they are equal, and again, you can see this really should be hydronium, but save some time, just say hydrogen. If the hydrogen ions and the hydroxide ions are equal to each other in concentration, then the solution is neutral. If there are more hydrogen ions than hydroxide, it's acidic. And if there's more hydroxide than hydrogen, it's basic. With conjugate partners that are in aqueous solution, so we're talking about an acid that has donated its proton, it would then have a conjugate partner on the other side of the reaction. So the acid donating its proton, that will happen to some extent, and the Ka value will tell you to what extent that happens. But the reverse of that can happen, where its conjugate partner can pick up that hydrogen, and because it's an equilibrium, that will be happening. And when the conjugate partner of the acid picks up its hydrogen, it's acting like a Bronsted-Lambert base, and it will have a particular Kb value for that process. And so it turns out that the Ka and Kb of any conjugate partners, and they have to be conjugate partners, but the Ka value multiplied by the Kb value of its conjugate partner will equal Kw, which we know is 1 times 10 to the negative 14. So what we can do then is, if we have the Ka value, we can find the Kb value of its conjugate partner, or vice versa, because Ka times Kb of any conjugate partners will give us this Kw value of 1 times 10 to the negative 14. Also, normal people don't like talking about scientific notation and concentration of hydrogen ions, and so as Soren Sorensen has done for us, he has converted this into a value that's a little bit easier to understand, known as pH, by taking the negative log of the hydrogen ion concentration. So this huge range, we have been logify them, and it's a negative log of those concentrations, and this gives us those pH values that we learned about in like grade school. We can reverse this process, and we can take the hydrogen ion concentration and find out, or we can take, the pH and find out what the hydrogen ion concentration is by doing 1 to the exponent negative pH value. So if you have your negative pH value of 7, let's say, you do 10 times 10 exponent negative 7, and you'll have 1 times 10 to the negative 7 moles per liter for the hydrogen ion concentration. Sig digs for this stuff, because it is a logarithmic scale, pH is a logarithmic scale, whatever the total number of significant digits in the concentration, so let's say you had like 2 values, so I don't know, your concentration was, let's say, 2.0 moles per liter. That's 2 significant digits, and so when you go to write the pH value, or you calculate the pH value for that concentration, note that the total number of sig digs in the concentration is the number of decimal places in the pH value. So that would give us a pH value, and we'd write point blank blank. We'd have our significant digits written after the decimal place, plus whatever the digit was for the pH value. Because it's a logarithmic scale, just realize logarithmic scales is they're talking about powers of 10, and so if you look at a pH of 7 versus a pH of 8 versus a pH of 6, when you do this jump between these pH values, 7 is 10 times more acidic than a pH of 8, and 6 is 100 times more acidic than a pH of 8. We can apply this same exact concept of pH to pOH. We can logify it as well, just make it a little bit easier to look at. And if you take the negative log of the OH, that will give you the pOH value, the power of the hydronium ions. And of course, we can reverse this process as well. If you have the OH, you can take 10 to the exponent negative of the OH and POH, sorry, and that'll give you the concentration of the OH values. So we won't get into deriving this equation. Lots of fun to look it up if you want, but we can relate pH and POH through pKW. This is the logified version of KW. So pKW, we know what KW is. It's 1 times 10 to the negative 14. Take the negative log of it, and that gives us 14. So pKW is 14, and pKW is equal to pH plus POH. So this gives us a very useful equation to quickly convert between pH and POH, because we know that the sum of those two numbers for any solution would be 14. So if your pH is 10, then you know your POH, sorry, it has to be 4, because the two of them have to sum together to give you 14. So that can be a quick way of going from POH to pH. So concentration of hydrogen ions, we know that there's a connection between it and pH, and again, Sorensen said, okay, no one wants to hear about the concentration of hydrogen ions, and said, let's turn this into a usable number, or a little bit friendlier number, I guess. And so taking the negative log of it will give you this pH value, going back several grades as to something, to a way of describing acids and bases. And we can undo this by taking 10 to the exponent of negative pH, and that'll give us our hydrogen ion concentration. We also know that there's a relationship between the hydrogen ion concentration and the OH concentration, because through that KW of water, any aqueous solution where these acids and bases are, there's going to be this equilibrium between the hydrogen ions and the hydroxide ions. So if you change one, we know how it will affect the other. And this is through this equation of KW. So KW is the product of the concentration of the hydrogen ions and the concentration of the hydroxide ions. And we know that for any aqueous solution at 25 degrees, this KW value, or the product of the hydrogen ion multiplied by the hydroxide ion, has to be 1 times 10 to the negative 14. So if you know that H ion concentration, you always know KW, so therefore then you could solve for the OH concentration. And of course, we can do the same thing to the OH concentration as we did to the H concentration. We can logify it and get our POH, doing the negative log of it, or we could go backwards and we could say, we could take the OH concentration and we could go to the POH. I think I got my arrows messed up here. This guy should be switched. But the exact same thing for pH, we can apply to the POH, and so we can talk about the hydroxide ion concentration, or the logified version of that. And now we also know that the sum of the pH and the POH, and so this corresponds to the KW here, the sum of the pH and the POH is going to equal 14. So if you knew you had a pH of 4, let's say, you had an acid with a pH of 4, then if you want to know the POH of that solution, because the pH is 4, then the POH, you'd know, has to be 10. So let's try this out. So if we had some nitric acid solution, and we know we could look at our Ka value and we'd say, okay, where's the Ka value for this nitric acid solution? But this is one of the strong acids. You can either memorize the strong acids, or you can look at your Ka table if you have it with you and say, okay, it's either not on there where they said it's very, very high, and without giving a number. So we're assuming that this is going to go to complete dissociation. So if we wanted to play around with doing some calculations between pH, POH, and OH, we can do it with this concentration here. Because it is a strong acid, we're assuming complete dissociation, and therefore if we have 0.02 moles per liter of the acid, then just like stoichiometry, 1:1:1 ratio, we are also going to get 0.02 mole per liter of hydrogen ions. Because the pH is based just on the hydrogen ions, that's really all we need to focus on. We don't need to think about the nitrate ions here. It's not going to affect the pH itself. More on that later. The hydrogen ion concentration is 0.020 moles per liter, so we can take the negative log of that, and we get a pH, a little bit easier to look at, 1.70, and because there are 2 sig digs in our concentration, we want to have 2 decimal places in our pH value plus whatever the number is in front of the decimal. Now it's also asking for our POH, so we have several ways we can go any way we want around that last circle there, but we know that the two of them, the pH and the POH, equals 14, so 14 minus 1.07 is going to give us a POH of 12.30. Now that we have the POH, we can use that quickly to find the OH concentration, and we can say 10 to the exponent negative 12.3 is going to give us 5 times 10 to the negative 13 moles per liter. And again, because we're going for 2 decimal places in the log version of the number, we should have a total of 2 sig digs in the concentration version of it. Another way of doing it is also we could have gone directly, we have the concentration of the hydrogen ion, and we could have gone directly to the concentration of the hydroxide ion with our Kw, because we know that Kw is going to equal our equilibrium expression, our concentration of hydrogen ions multiplied by the concentration of hydroxide ions. And so we know Kw is 1 times 1.0, let's go 2 sig digs, times 10 to the negative 14 equals, we already know our hydrogen ion concentration of 0.02 moles per liter. And so we could solve for our hydroxide ion concentration that way and get the same answer. The way you do it is going to work out. So we have this relationship again between pH, pOH, OH, and hydrogen ion concentration. So let's try calculating the pH. Given a base, and we have same concentration, 0.02 moles per liter of this hydroxide ion. This is lithium hydroxide, so we're doing a full dissociation here. So whatever our concentration of lithium hydroxide will give us an equal concentration of hydroxide. Therefore, we have 0.02 moles per liter of this hydroxide ion. We can take the log of that, and this will give us our pOH, which we know if we add it with our pH, which is what we're looking for, so we're going to solve for pH. We have 14 minus pOH will give us our pH, and this gives us our pH of 12.3 because we only have 1 sig dig in our concentration. We should have 1 decimal place in our pH value.